Welcome to this IC engine and gas turbine classes. In this video lecture, we will be discussing about the Otto cycle on which petrol engine or the spark ignition engine generally works. এর আগের ভিডিওতে আমরা যেটা আলোচনা করেছি সেটা হচ্ছে কার্নট ইঞ্জিন এবং কার্নট সাইকেল সম্পর্কে আলোচনা করেছি, কিন্তু আমরা দেখব যে কার্নট ইঞ্জিনে কোনো রকম কোনো প্র্যাকটিক্যাল যেসব ইঞ্জিন আমরা দেখতে পাই আমাদের চারপাশে সেই ইঞ্জিনগুলো অপারেট করে না। তো এর কিছু কারণ আছে, যেটা কার্নট ইঞ্জিন যেটা জেনারেলি সাডি কার্নট যে ইঞ্জিনটা প্রপোজড করেছিল এবং যে সাইকেলগুলো কার্নট ইঞ্জিনে আছে দ্যাট আর জেনারেলি আইডিয়াল সাইকেলস, ওকে। অ্যান্ড এই কার্নট ইঞ্জিন জেনারেলি প্র্যাকটিক্যালে আমরা ইমপ্লিমেন্ট করতে পারি না, এর কারণ ডিউ টু ইটস হাই ভলিউম অ্যান্ড দ্য প্রেশার রেশিও। তো এই জন্য প্র্যাকটিক্যালি যে ইঞ্জিনগুলো পেট্রোল ইঞ্জিন বা স্পার্ক ইগনিশন ইঞ্জিন বা ডিজেল ইঞ্জিন, যে ইঞ্জিনগুলো এয়ার স্ট্যান্ডার্ড যে সাইকেলগুলোর উপর চলে তার মধ্যে একটা হচ্ছে অটো সাইকেল। এবং অটো সাইকেলটা আমরা জানি যে পেট্রোল ইঞ্জিনের যে ওয়ার্কিং প্রিন্সিপাল সেটা অটো সাইকেলের থার্মোডাইনামিক্যালি অটো সাইকেলের উপর বেসড করে চলে, ওকে। অ্যান্ড ওয়াই দিস সাইকেল অর দ্য cycle of the petrol engine is generally called Otto cycle? Because it was generally proposed by the scientist Nicholas Otto. That's why it is called the Otto cycle. আমরা যদি এর আগের যে ভিডিও লেকচারস আছে, if we recapitulate that particular topic, that is the Carnot cycle, then we will be able to understand the modification of Carnot cycle, and that modification of the Carnot cycle is generally related to this Otto cycle, okay. Now let me draw the PV diagram, basic PV diagram, which we have already discussed in our previous video. PV diagram of the Carnot cycle, okay. This is the PV diagram of Carnot cycle, and you can see this is the Carnot cycle PV diagram, and we know there are four processes, two adiabatic process and two isothermal process. One is the isothermal expansion. If we draw, this is 1 to 2 is the isothermal expansion, and then adiabatic expansion 2 to 3 is the adiabatic expansion, and then the isentropic, we can say isentropic, this is not isentropic, isothermal compression. This is the isothermal compression 3 to 4, and 4 to 1 again is the adiabatic compression. Adiabatic compression, this is the cycle of the Carnot cycle, PV diagram of the Carnot cycle. এবং নিকোলাস অটো যে সাইকেলটা প্রপোজ করেছিল, that is the modification of the Carnot cycle, if we can say. That is these two, if we can say this is 1 to 2, this process is the isothermal heat addition process, we can say in Carnot cycle, and this is the isothermal heat rejection process, we can say this is the isothermal heat rejection process, ঠিক আছে। তো এই হিট অ্যাডিশন এবং রিজেকশন এই দুটো প্রসেসকেই নিকোলাস অটো মডিফাইড করে একটা সাইকেল প্রপোজ করেন, অ্যান্ড দ্যাট ইজ কল্ড দ্য অটো সাইকেল, ওকে। তাহলে আমরা যদি এই ডিফারেন্সের মধ্যে দিয়ে দেখি বা এই মডিফিকেশন ভার্সন অফ দ্য কার্নট সাইকেল দেখি, তাহলে দেখব যে অটো সাইকেলের ক্ষেত্রে কি হয়েছে, এই যে অ্যাডিশন প্রসেস আছে, ঠিক আছে, আইসোথার্মাল হিট অ্যাডিশন প্রসেস, দিস ইজ দ্য কিউএস কি সাপ্লাই, অ্যান্ড দিস ইজ দ্য কিউআর। এই আইসোথার্মাল হিট অ্যাডিশন প্রসেস এবং আইসোথার্মাল হিট রিজেকশন প্রসেস, এই দুটো প্রসেসকে কনস্ট্যান্ট ভলিউম প্রসেসে ট্রান্সফার করা হয়েছে ইন কেস অফ অটো সাইকেল। সো ইফ উই ওয়ান্ট টু ড্র দ্য অটো সাইকেল, ওকে, পিভি ডায়াগ্রাম অফ অটো সাইকেল, দেন we will find that these two process, okay, these two process is generally this is 1 to 2, this is the heat addition process, and this is at the constant volume process, and these two, let me draw these two, this is the heat addition process, and we will be discussing all the processes. Let me just first identify the modification of the Carnot cycle, okay. This is the Carnot cycle, isothermal heat addition, isothermal heat rejection, and you can see this is 1 to 2 process. This 1 to 2 process get changed into the constant volume process. In case of Carnot cycle, this is the isothermal heat addition process, and this is also the 3 to 4 process is generally isothermal heat rejection process. But in case of Otto cycle, we will be generally we will find that this 1 to 2 process is generally constant volume heat supplying process or constant volume heat addition process, and this 3 to 4 is generally heat rejection process, and that is at the constant volume process. Okay, and this is the basic modification, okay, or we can say the basic difference between the Carnot cycle and the Otto cycle. All other processes are generally same. We can say this is the reversible adiabatic process, or we can say the isentropic compression process. We will be discussing that. 1 to 2 process is the constant volume heat addition process. So the motive of these two diagram is to show the differences between the Carnot cycle and the Otto cycle. Okay, তো Carnot cycle কি হলো, isothermal heat addition হলো, কিন্তু Otto cycle দেখা যাচ্ছে that is the constant volume heat addition process. The volume is constant. In case of this Carnot cycle, the temperature is constant, and that is the main constraint. Okay, volume is not constant in this Carnot cycle. That's why it is not possible to implement this cycle, okay, in practical. Okay, that's why this cycle is generally preferred, the cycle which generally had been proposed by the scientist Nicholas Otto. Okay, this is the basic difference between the Otto cycle and the Carnot cycle. Okay, or we can say the Otto cycle is the modified version of the Carnot cycle. Now let us recapitulate the 4 processes that is which are generally associated with this spark ignition or petrol engine. Okay, we know the 4 processes are suction, compression, and then the expansion, and then the exhaust. এবং এই যে 4টে প্রসেস আছে, এই 4টে প্রসেসকে যদি আমরা থার্মোডাইনামিক্যালি আমরা কোনো সাইকেলে ডেপিক্ট করতে চাই এবং দেখব যে এই সাইকেলটা কোন এবং কোন এই ইঞ্জিনটা বা এই প্রসেসগুলো কোন সাইকেলের উপর দিয়ে হচ্ছে, তখন আমরা দেখব দ্যাট ইজ জেনারেলি অটো সাইকেল. ওকে, so first in order to understand the Otto cycle, let me draw the PV and the TS diagram of the Otto cycle, and then we will be explaining the term associated with this Otto cycle, or the processes, different processes that are generally associated with this Otto cycle. Okay, so first এটা হচ্ছে PV diagram. As we have already discussed, there are 2 heat addition process. This is the 1 to 2. This is the heat addition process, and this heat addition process is at constant volume. Okay, this is state 1 and this is state 2, and this is the heat addition process. Then the expansion process. Then the what kind of process is this? Then the process is generally called the expansion process. This is the expansion process, and 2 to 3 is the expansion process, and this is reversible adiabatic expansion. Okay, or we can say this is the isentropic expansion process, and then the process is generally 3 to 4 is the process which is generally heat rejection process, that is again at the constant volume process, and 4 to 1 that is generally compression process. We can say this is the compression process, 4 to 1, or in reverse way we can write in this way, that is this is the 1 to 2 process, compression process, that will be generally easy to understand. Okay, and 2 to 3 this is the heat addition process, and 3 to 4 is the expansion process. Okay, 1 to 2 is the process compression process, 2 to 3 is the heat addition process, 3 to 4 expansion process, and 4 to 1 is the heat rejection process. This 2 to 3 is nothing but that is the heat addition process, and this 4 to 1 is process of heat rejection. Okay, and we can also draw this 0 to 1, and which is suction process. We can say this is the suction process. So if we want to write down these processes, 0 to 1 is nothing but the suction process. Okay, suction process, in which in case of this is the cycle for the petrol engine, and this cycle is used for the petrol engine. That's why air fuel mixture is generally drawn into this process, and total air fuel mixture is generally treated as air in a case of this cycle, whenever we will be generally driving the equation of the efficiency, or considering the different ideal processes, then we will be consider the air fuel mixture as the air. Okay, and then 1 to 2, what kind of process is this? This is generally reversible adiabatic compression process. We can say reversible adiabatic we know what is reversible and what is adiabatic process. We have already discussed in the Carnot engine or Carnot cycle reversible adiabatic compression process, okay, which is also called the isentropic process. Okay, this is reversible adiabatic compression process, or we can say this is isentropic process. Isentropic process, the process in which entropy remains constant. Okay, this is the isentropic process. And this 2 to 3 is the process, that is the heat addition process. Heat addition process, and the process in which heat is added to the cylinder, okay, engine cylinder, or the combustion generally takes place at this process. Okay, heat addition process at constant volume, or we can say isochroic heat addition process, or we can say that this process is isochroic heat addition process. And then 3 to 4 is the process, again this is the reversible adiabatic expansion process. And this is the expansion stroke from which we generally get power. We generally get power from this process, this 3 to 4 process. This 1 to 2 is the process on which we generally deliver the work, and 3 to 4 is the process, expansion process, from which we generally get the power. Okay, that is the basic difference between these two processes, 1 to 2 and the 3 to 4. Reversible adiabatic expansion process, or it is also called the isentropic expansion process, or we can say this is isentropic expansion process. Isentropic expansion means in which the pressure decreases and volume increases. The isentropic, if we want to define this isentropic compression process, then it will be like this: in the process in which pressure generally increases and volume decreases. Okay, and next one is the 4 to 1 process. 4 to 1, this is the heat rejection process. This is the heat rejection process at constant volume. Okay, and this is these are the 4 main process that are generally taking place inside the Otto cycle. Okay, in the Otto cycle. Okay, now let me draw the volumes. This is the V1, that is generally equal to V4, and this is V3, which is equal to V2, and this V3, okay, or V2, this volume at V3 or V2 is generally called V3 is equal to V2 is nothing but the clearance volume. This is the clearance volume. Okay, and V1 is equal to V4, which is generally called nothing but the total volume of the cylinder. Okay, this is the total volume of the cylinder. Okay, and from this we can generally derive the equation of the compression ratio, which is generally denoted by R, compression ratio. Then the compression ratio will be denoted by this R, and this is nothing but that is V1 by, we can say this is the V1, this is the V1 total volume by the clearance volume, V1 by V2, or is equal to V4 by V3. This is the equation for the compression ratio, and which will be needed for driving the for calculating the efficiencies of this Otto cycle. Okay, and this is the PV diagram. These are the 4 processes related to this PV diagram. Okay, which is generally this Otto cycle is generally modified version of the Carnot cycle. Okay, now next let me draw the TS diagram. Okay, let us see the TS diagram. What will be the nature of the TS diagram? Okay, now if we draw the TS diagram, okay, temperature entropy diagram, then it would be like this. This is 1 to 2 process. 1 to 2, what kind of process is this? This is the isentropic expansion process, in which we can say thermodynamically this is PV gamma is equal to constant, PV to the power gamma is equal to constant. Gamma is nothing but that is the ratio of specific heats, that is Cp by Cv. Okay, specific heats at constant pressure divided by the specific heats at constant volume. Okay, now TS diagram, first 1 to 2 process in which isentropic, the process is isentropic in which entropy remains constant. So we can say this is the TS diagram, entropy remains constant in this process 1 to 2. Okay, let me write down here also, this is S is equal to constant, this is S is equal to constant, and in this case V is equal to constant, in this case V is equal to constant, as we can see from this diagram clearly. Okay, and from this diagram we will see the temperature relation between temperature and this entropy. Okay, how entropy and the temperature changes with this cycle. 1 to 2 process, entropy remains constant, the entropy remains constant, and then 2 to 3 process is the process, 2 to 3 process is the heat addition process. You can see this is the heat addition process in which temperature generally increases. Okay, this is the 2 to 3 process, I can write this 2 to 3 process in which temperature increases because heat addition is taking place at constant volume. Okay, and in this case V is equal to constant, volume generally in this case is constant. Okay, and 3 to 4 again reversible adiabatic process. What kind of process? That is reversible adiabatic compression process. We can say this is generally not the compression process, this is the reversible adiabatic expansion process 3 to 4. Okay, in which entropy remains, again entropy remains constant. Okay, in this case entropy remains constant, this is 3 to 4. And at last the process, that is the heat rejection process at constant volume in which temperature decreases. Okay, so this is the process of heat rejection, 4 to 1 process heat rejection, that is also at constant volume. Okay, and these are the basic PV and the TS diagram of Otto cycle. Okay, PV and TS diagram of Otto cycle, and from which we can generally understand how the different processes is generally taking place. Okay, and that can be found out from this PV and this TS diagram. And now let us drive the efficiency for this Otto cycle. Okay, now let me clear this board first. Okay, there are 4 processes. One is the reversible adiabatic compression process 1 to 2, and then the process is the heat addition process, constant volume heat addition process. 3 to 4 is the process reversible adiabatic expansion process, or we can say the isentropic process in which PV to the power gamma is equal to constant. Okay, and next one is the 4 to 1 process, that is the heat rejection process at the constant volume. Now if we want to calculate the total work done or the net work done, okay, if we want to calculate the net work done, then W net will be like this, that is QS minus QR. Okay, what is QS? QS generally 2 to 3 points at the process of 2 to 3 the total heat supplied. Okay, which can be generally find out, that is at the constant volume. Okay, so we can say if there is m mass of gases, okay, m mass of air, and that is the specific heat of the air is Cv, okay, at constant volume, then we can write mCv T3 minus the temperature at state 3 minus temperature at state 2, T3 minus T2, and QR will be like this. This is mCv, again the heat rejection process, that is 4 to 1 process is the heat rejection process, we have already depicted that, and this will be like this T4 minus T1, and the difference in between these two, QS minus QR, will give us the total net work done. Okay, and how to find out this efficiency? If we want to find out this efficiency, then it will be like this: N Otto is equal to eta Otto is equal to QS W net by heat supplied. Okay, that is the net work done by heat supplied. Heat supplied is nothing but that is QS. Okay, and W net is equal to QS minus QR by QS. Okay, this is the equation, basic equation. Okay, you can find out this. This will be 1 minus QR by QS. Okay, and that will become 1 minus QR is equal to nothing but that is MCB T4 minus T1 divided by MCB T3 minus T2, and finally it will become T4 minus T1 by T3 minus T2. This is the equation for the Otto cycle. Okay, equation for the efficiency of the Otto cycle. Now if we want to simplify this equation, or in other term, if we want to express this equation in terms of the compression ratio, then we have to do some extra work. Okay, and let me do that. Okay, we want to generally calculate whole this efficiency in terms of compression ratio. So if we consider this process 1 to 2 and 3 to 4, okay, considering process 1 to 2, considering process 1 to 2, we can write down this from the ideal gas equation. Okay, different ideal gas equation, we can write this, that is T2 by T1 is equal to nothing but that is V2, sorry, this will become V1 by V2 to the power gamma minus 1. Okay, as we know, the PV gamma is equal to constant, and this equation will become, for this 1 to 2 process, this will be become P1 V1 to the power gamma is equal to P2 V2 to the power gamma, and there are again another equation, that is T1 by T2. From this equation we can derive this. Okay, T2 by T1 is equal to V1 by V2 to the power gamma minus 1, and again for the process 3 to 4 we can write down this, that is T to the power 3 by T to the power 4 is equal to V to the power 4 by V to the power sorry, this is not T to the power, that is T3 by T4 is equal to V4 by V3 to the power gamma minus 1. Okay, now you can find this V1 by V2 is nothing but this is the compression ratio, okay, which we have already defined, and this V4 by V3 is again compression ratio. Okay, so we can write this two term is generally equal, so we can write this T2 by T1 is equal to T3 by T4, or from here to here I am writing this, that is we can write this T4 by T3 is equal to T1 by T2, or from this আমরা জানি এটাকে আমরা from this we can derive, that is equal to this is equal to nothing but T4 minus T1 by T3 minus T2 যদি আমরা অনুপাতের নিয়ম অনুসারে করি, and that will become this. Okay, so we can write this is the from this equation we can derive this. Okay, that is T4 by T3 is equal to T1 by T2 is equal to T4 minus T1 by divided by T3 minus T4. Okay, now we can rewrite this equation. Okay, this equation T4 minus T1 by T3 minus T2, we can rewrite this equation as from this we can rewrite this equation, and this equation will become 1 minus, okay, let me generally make some space for this. Okay, let me write down this here. Okay, write down this here, this will become 1 minus nothing but T1 by T2. Okay, as we have proved, that is T4 by T3 is equal to T1 by T2 is equal to T4 minus T1 divided by T3 minus T2. Okay, তাহলে আমরা এটাই অবশ্যই লিখতে পারি যে T4 minus T1 এই ইকুয়েশনে কি ছিল 1 minus T4 minus T1 by divided by T3 minus T2, তাহলে আমরা এটাকে লিখতে পারি 1 minus T1 by T2. Okay, and this is T1 by T2. What is T2 by T1 is generally compression, generally that is the V1 by V2 to the power gamma minus 1. So if we want to depict this equation in terms of compression ratio, then we can write this, okay, 1 by T1 T2 by T1, or 1 minus 1 by V1 by V2 to the power gamma minus 1, and finally it will become 1 minus 1 by R to the power gamma minus 1, and this is the equation for Otto cycle. Okay, now we have derived the efficiency of the Otto cycle in terms of compression ratio. Okay, now let me focus on the equation of this Otto cycle, efficiency of this Otto cycle, the equation for the efficiency of this Otto cycle. Okay, so we have derived the eta Otto is equal to 1 minus 1 by, that is the R is nothing but the compression ratio, R to the power gamma minus 1. Okay, this is the efficiency for the Otto cycle. Now we can see the efficiency of the Otto cycle is generally depending on the compression ratio. যদি আমরা compression ratio বাড়াই তাহলে দেখবো যে আমাদের এফিসিয়েন্সি যে অটো সাইকেলের বা পেট্রোল ইঞ্জিনের যে এফিসিয়েন্সি আছে দ্যাট উইল বি ইনক্রিজড, এবং যদি আমরা কম্প্রেশন রেশিও কমাই তাহলে আমাদের যে এফিসিয়েন্সি আছে সেটা কি হবে, সেটা জেনারেলি কমে যাবে। ওকে, তাহলে আমরা দেখছি এই যে যেটা আমরা দেখেছিলাম কার্নট সাইকেলে, ওকে, ইন কেস অফ কার্নট ইঞ্জিন, কার্নট সাইকেলে আমরা যেটা দেখেছিলাম যে এফিসিয়েন্সি যেটা আছে কার্নট ইঞ্জিনের, দ্যাট ইজ জেনারেলি ডিপেন্ডেন্ট অন দ্য টেম্পারেচার অফ দ্য সোর্স। ওকে, মানে থার্মাল রিজার্ভার যেটা সোর্সে ছিল তার টেম্পারেচারের উপর দিয়ে তার যে এফিসিয়েন্সি আছে কার্নট ইঞ্জিনের এফিসিয়েন্সি সেটা ডিপেন্ড করছিল। কিন্তু আমরা অটো সাইকেলের ক্ষেত্রে দেখব যে হিট অ্যাডিশন কতটা হচ্ছে বা রিজেকশন কতটা হচ্ছে, যে টোটাল হিট অ্যাডিশন বা রিজেকশনের উপর কিন্তু অটো সাইকেলের যে এফিসিয়েন্সি সেটা ডিপেন্ড করছে না, অ্যান্ড দ্যাট ইজ অনলি ডিপেন্ডেন্ট on the compression ratio. Okay, and to some extent on the specific heat ratio, that is the gamma. Okay, specific heat ratio যদি আমরা কোনো রকমের ওয়ার্কিং ফ্লুইড ইউজ করি যার স্পেসিফিক রেশিও বেশি আছে, দেন it will also increase the efficiency of the Otto cycle. Okay, so this is the equation for the Otto cycle. Okay, and next now we will be generally discussing about the work done and the mean effective pressure of this Otto cycle.